So I would like to thank the organizers for the honor to present a talk at this conference. I think that the fact that this conference happens is a manifestation of general optimism that mathematics in the future will develop in the same way as it was developed before. And in preparing this talk, I started to think that maybe I should invent for this conference some new problems and explain that to many people that the progress in these problems will be significant for many other cases, many other situations, and naturally I did not succeed. And instead, I started to think about the past of the theory of dynamical systems. And I came to the conclusion that we have many interesting moments, many interesting phenomena in the past, which, if this phenomena will persist and will happen in the future, then certainly we can expect serious progress in various directions. So one of the first conclusion is that in the theory of dynamical systems, in its basic stream, we had several striking discoveries, after which new methods, new ideas appeared, and many problems which were considered before as absolutely difficult become not trivial, but at least treatable. And it is easy to write the list of these great events in the theory of dynamical systems, and I shall write them in more or less chronological order, because my topic will be somehow connected with all these happenings in the past. So I write first KAM theory. KAM stands for Kolmogorov-Arnold-Moser theory. I shall not formulate its essential meaning. Maybe I shall say about it a little bit later. Then the second is so the works of Smale, Anosov, and others about hyperbolic dynamics, strange attractors, and especially I want to mention as a one very well-known case is Lorentz model. And the reason why I mention it separately is because after Lorentz model became known, all theory of dynamical system, what is called now in physics literature the theory of deterministic chaos, got very many applications in physics, in biology, and in other sciences. Then the third topic is entropy theory, which started with the work of Kolmogorov and ended essentially ended essentially with the works by Ornstein and his colleagues. And it was very important that these two directions existed more or less at the same time, and they somehow helped to each other, and their connections led to something which can be just described as connections of the chaos theory. With statistical mechanics. And then the last topic which I want to mention is Feigenbaum Universality. And maybe many of you know that, first of all, it was observed numerically, and just numerics, first of all, showed that the sequences of period doubling bifurcations persist in many families of dynamical systems, and then Feigenbaum numerically observed that the corresponding iterations of transformations look approximately the same. And after that, the connections with the normalization group theory in statistical mechanics appeared. It was used in the works of Feigenbaum himself and Tresset, Collet and Tresset, and some others. And about this topic, I want just to say that if some traces of problems which are in 1, 2, 3 we can find in the past, then this topic was completely unexpected, and the approach to dynamical problems which was used in this case was also absolutely new, and probably this is some kind of example which can happen in the theory of dynamical systems, that some new ideas arise from the interaction of computer mathematics and theoretical investigations, and new understanding comes. So, if we think about these 4 topics, then now it is clear that it is difficult to invent something. For example, if you would ask any mathematician at the beginning of 40s, what does he think on the development of the theory of dynamical systems, then I'm quite sure that nobody would mention any of these topics. Therefore, it means that what one can hope mostly in talks like this is to discuss possible directions where we can expect some serious progress with new ideas and new results of general nature. And for these 3 topics, I prepared the following, which I shall discuss in detail. That the one which I formulate in the following way is hyperbolic and quasi-periodic types of motions are generically the only stable types of dynamics. I don't write down here precise definitions because it can be different in different situations, but I shall discuss in detail some concrete problems which we encounter when we think about this general problem. The second direction can be formulated as follows. Partial differential equations as dynamical systems and another subtitle which is equivalent is qualitative theory of partial differential equations. Mostly, but not necessary. Just general formulation can be even in other cases. And then the third topic is quantum chaos. And here are people who can say more about this, especially I hope that Peter Sarnak will comment, will make several comments about this either today or later when he will speak on Sunday. And so I shall start to discuss basic concrete problems which appear if we think about it. So concerning this general question that nothing else like hyperbolic and quasi-periodic dynamics appears, one can say the following, that in case of a Hamiltonian system, it means that the phase space M can be decomposed onto three parts, M1, M2, M3. M3 is negligible, and the most mild form of this assumption is to say that its Liouville measure is equal to 0. And M1 consists of invariant tori with quasi-periodic motions on each of them. And M2 says that consists of components of positive measures, with non-zero Lyapunov exponents. This is just a precise formulation in the case of Hamiltonian system, but one can give a similar formulation in the case of dissipative system, where we don't have a priori an invariant measure, and we can just replace the property of positive Lyapunov exponent by some properties of hyperbolicity. I shall speak about this a little bit later. And there exists even the whole program, which was initiated by Jacob Pellis, whose main purpose is to show that if we consider generic vector field, then it has some generalized hyperbolic property on the limiting points of dynamical systems. Yeah, in generic dissipative systems, there are no tori. Yeah, this is finite dimension. Yeah, in this topic, I am certainly consider finite dimensional case. But if we think about this general statement which is hidden here, then we can see that it has a great impact on many problems, for example, in differential geometry or in statistical mechanics. The fact that any Hamiltonian system consists of quasi-periodic motions and dynamics with continuous continuously back spectrum is a very strong statement for some questions which are considered in statistical mechanics for dynamical systems with many degrees of freedom.
When you say genetic, you refer to the Hamiltonian also, or just?
I don't want to answer to this question because the notion of generic behavior is different in different situations. In the case of Hamiltonian system, for example, we can assume that these sets are generic if the measure of the complement is 0. But we also must assume something about generic behavior of Hamiltonians and other things. And this is the part which I don't want to specify. I just want to describe the general phenomena which we can have. So if we think about this problem in more detail, then we certainly must consider some examples, some first examples where we can check this hypothesis and try to see the results which are in favor or against this theory. And there is, luckily enough, there is one example which is called twist map, which was studied before in many detail. So let me describe this example. It is the space of transformation of two-dimensional cylinder where the coordinates on the cylinder are z and phi. Z is the vertical coordinate, which is interpreted as amplitude. Phi is the phase. And the transformation has the following form. Z prime is equal to z plus kappa v of phi, and phi prime is equal to phi plus z prime. Here I must write modulo 1. And v of phi is smooth periodic function of period 1. And when v is sine of phi, this is called standard map, but in the theory of dynamical system, but it was known much before in the in statistical mechanics under the name of Frenkel-Kontarova model. And this type of transformation was considered by John Mather and Aubry and Serge Aubry for extension, for some kind of extensions of Kolmogorov-Arnold-Moser theory, where they constructed invariant sets which appear after invariant curve of KM theory and disappear. And so now certainly in studying examples of this type, we must first of all to check what KM theory can say about the basic problems. So KM theory existed for almost 50 years. The corresponding technique is very well developed. And there are recent papers where we have new methods to write analytic expression for invariant tori. And all this leads to conclusion that there is nothing new which we can expect from KM theory. What I want to say is that KM theory gave possibility to prove some number of results and gave us some methods to prove the results, but at the same time it led to several new problems, and it is a general belief that KM theory cannot say anything about these new problems. And I want to describe the problems which remain after KM theory. So I can describe them in the following general term. Construction of non-smooth invariant sets. So what the most advanced statement of Kolmogorov-Arnold-Moser theory can be formulated as follows. Suppose that we have a curve which is given by a nice function f. Z is some nice function of phi. And the curve given by this equation is invariant under our transformation. And suppose that the function f has three derivatives and the rotation number is Diophantine. This word was used today several times, so I shall not repeat its exact definition. So then the Kolmogorov-Arnold-Moser theory says that this curve is a density curve of other invariant Km curves, which comes to this one from both sides. So if this is the original curve, then it is the density point of other invariant curves, which comes to this one from both sides, from below and from above. But if we look at if we look at general picture of dynamics for the standard map, then we come easily to conclusion that the general structure is the following, that there are invariant curves of this type, and then there are open domains which may have non-trivial invariant sets inside, but at the same time they have trajectories which in some sense are dense on this set. And therefore, from this picture, which follows from all numerical experiments, it follows that there are invariant curves for this simple standard map, which are limits of other invariant curves only from one side. In other words, in this picture, the invariant curve can come from below, but cannot come from above. And by this reason, they cannot be invariant curve of Km theory, and therefore they are not smooth. And there are some theorems which are based on Birkhauser theorem, which says that essentially this function f must belong to some class 1 plus alpha. And we don't know how to construct this curve. From the other side, if you look at any numerical picture, you see them. I shall say about possible construction of this curve a little bit later. But now I want to formulate for this case of system, for this case of maps, another problem. So if this is say A, then this is B. Classification or description of all KAM islands. What does it mean, KAM island? It is a domain bounded by some closed curve such that this domain is periodic under the action of our transformation, and again inside this domain we have many invariant curves, so that the area occupied by this curve inside this domain is positive. And again, by the same reasons as before, the boundary of this Kolmogorov-Arnold-Moser islands is a curve which cannot be smooth. And this is another example of non-smooth invariant set which belongs to the same class as in the previous case. Let me go a little bit further and to describe what does it mean classification. Classification means that all these islands have some kind of hierarchical structure. And this hierarchical structure can be described in the following way. Suppose that we have an island of this type. Then around these islands, there are islands of a smaller scale, but of the same structure as the original one. Then this island is periodic with a corresponding period, and near this island there are smaller islands which are periodic with a longer period, which is a product of period of this island times some other number. But the crucial observation, which is not again a mathematical theorem, but just numerical results or result of some qualitative consideration, is the following: that if we consider the whole hierarchy of these islands, then there is some scaling property. And this scaling property means that if we consider the neighborhood of each of these islands, whose size is of the order of the distance to the next island, and consider the corresponding iteration of our map, then this iteration belongs to some open sets of transformation which produces the same islands. And if this is so, then then we can really then we can hope to prove the existence of all these infinite trees of islands along some maternal islands, and this whole structure exhausts all possible islands in the transformation of this type.
How individual islands are unstable? Because the system island may be rearranged. The individual non-smooth curves are unstable.
No, they are stable, but their rotation number changes.
Like if you change a little bit transformation, they stay.
Yeah, they're stable, yeah.
So the lack of smoothness is because of that rotation?
Yeah, it is, no, it is because it is a boundary curve of the island. If it were a Kolmogorov-Arnold-Moser curve, then it would be density points from both sides of other invariant curve. But since for the islands we don't have other invariant curve outside, then it cannot be smooth. Yeah, but they are stable in the sense that if we change parameters or perturb the function v, then these islands exist. They just move a little bit, but they remain unsmooth.
The whole hierarchy is stable, or smaller maybe unstable.
The whole hierarchy is stable.
I mean, it's numerical, or you can prove.
No, nothing is proven. There are some qualitative arguments which show that this is so, but it's not a
The
theorem.
stability of islands, it's a no.
It is not, well, some hierarchies are constructed in the works of Melnikov, but they describe only some part of this picture. So he constructed the islands where the hierarchies of islands when the period grow with the number of islands. Then these smaller islands comes closer and closer to the previous islands, and this is slightly simpler. So all these problems can be studied, apparently, with the help of renormalization group theory. Or renormalization group analysis. And this is the main hope for attacking these problems. And the basic idea of this analysis is just as in the case of Feigenbaum universality. And it says that when we consider islands of small size, then the structure of the whole transformation is irrelevant. And if we consider the formulas for the transformation, then they converge to some universal form. This universal form is not known, and the stability property of this renormalization group is not known, but it is, from general picture, it is clear that it has to be so.
It's again, we can finite dimensional function space with finite dimensional attractive.
Yeah, yeah.
It's more equal dimensions in one or more?
I think it should be certainly only one because, yeah,
Like a Feigenbaum.
like in Feigen, yeah, that's. No, actually, well, this is a rather subtle question because the answer to this question depends in which space you consider the action of renormalization group transform. If you reduce this space sufficiently well, so just remove all unneeded parameters, then it becomes one. So, but another problem which appears in this case, which I shall formulate in the following way, importance of Mr. Tau. Tau is golden mean. And this number appears in the theory of dynamical system in the following way. If we consider all transformation of this type, then the invariant curve, which I described before, exists until the parameter kappa is small enough. But when kappa reaches its critical value, kappa critical, then there is a moment when there exists only last invariant curve. This invariant curve again cannot be Km curve because it is isolated curve. And it was a remarkable numerical discovery by John Green. And then there was some theory which was constructed by Robert Mackay, which says that for this invariant curve, the rotation number is golden mean. And also there are physical theories which say that the rotation number of all boundary curves corresponding to KM islands must be also very special. They are not necessarily golden mean, but in the expansion into continuant fraction, the element of this continuant fraction must be constant standard with this. So they just correspond quadratic irrationalities. Yeah, independent of it's a property of renormalization group theory. It's not the property. It's a property of universality class which corresponds to this case. Yes. Then, so I can talk about this, the property of standard map for a very long time. Even the time allowed by Vitaly will be far from being enough. But so, but I just want to say about this family of maps which I wrote before, the following. That there is one class of systems where we can prove practically all hypotheses. Sometimes it is very difficult, requires some time, but eventually everything is solved. And almost all problems were solved for the family of quadratic maps, A minus x squared. So recently, for this one so it is a very simple family of maps, and initially there was a lot of numerical experiments with this map. For example, the so-called Mandelbrot set was discovered if we consider complex values of A and other numerical results. Recently, there were remarkable theorems proved independently by Lubitsch and Gracek and Sviontek. which says the following. Suppose, so the parameter A lies within the interval 0 to 4. This is the natural set of values of A. It can be decomposed again on two sets. One is, so the sets A1, A2, A3. The Lebesgue measure of A3 is 0. The Lebesgue measure of A1 and L2 is positive. And for A belonging to A1, this transformation, TA, has a stable periodic orbit. It means that almost any point of this interval is attracted to a finite set as the number of iteration tends to infinity. And for A belonging to A2, we have a chaotic type of behavior, meaning that the transformation T of A has an invariant measure with a density depending on X. And this is the theorem. So Jacobson proved a weaker version of this theory, which says that the set of A where such a density exists has positive Lebesgue measure. And Mishalevich and Grachik and Sviontek proved that the complement to the set of values of A where this measure exists consists essentially of those A where we have stable periodic orbits. So we can consider the family of the standard family as some kind of two-dimensional generalization of one-dimensional maps. And if we follow this analogy, then we can formulate the following conjectures, or the following statement, the following conjectures. So the whole set of parameters consist of three parts again. No, that's the standard map. So even yes, twist map. So this is the family of maps depending on one parameter kappa, and this space of parameter kappa can be decomposed onto three parts. So kappa 1 or A1 is the set of kappa where kappa where T sub kappa has no islands. This is the analogy of the set A2 in the case of one-dimensional map. It means that in this case, the whole transformation has positive Lyapunov exponent and is ergodic and stable.
Was it the Janet, but there was not Beast?
Huh?
Beast was the Janet, so KM does what?
The K, yeah, Km does that. It's for sufficiently large K. And A2 consists of those cases where T of kappa has islands and sets of positive measure with positive Lyapunov exponents. So about the first hypothesis, we worked with Kosygin, but our attempt is not finished yet. The problem seems, so the problems to prove that the set A1 has asymptotic density equal to 1 seems to be very difficult. And about problem concerning A2, conjecture is that the set A1 has density, asymptotic density 1. In other words, if we choose randomly the value of kappa in a large interval value of kappa, then this transformation has no islands at all and consists of a single ergodic component. No, it's also not known. No, but maybe it is simpler to prove that it has density 1 than it is non-empty. A3 is just the complement. And it has measure 0.
That's a theorem or part of the conjecture?
It's part of the conjecture. A3, which is a complement, by the analogy of the set. So, so now I stop with problem number 1, and I want to spend 10 minutes talking about dynamical system related to partial differential equations, in 5 minutes about quantum case, and then we shall have discussion. There's dynamical system. So, in my opinion, the representation of shifts along trajectories, along solutions of partial differential equation as a vector field in infinite dimensional functional space is not that fruitful, because the space is huge and it has no topological properties. That's the first remark. The second remark is that, in my opinion, the number of nonlinear partial differential equation is very limited. So Misha explained today that the number of algebraic manifolds is very limited, but in my opinion, the number of nonlinear partial differential equation is even less, and even more. Nonlinear differential equations, which have some meaning, have also some names. Nonlinear Schrödinger equation, Korteweg-de Vries equation, Navier-Stokes equation, no-reaction diffusion equation, Kuramoto-Sivajinsky, and this probably almost all, well, we can add a little bit more, but not too much. And so, in my opinion, the basic questions which we asked about vector field on the manifold are not relevant. And the most important problem is to construct particular classes of solutions. So since the dynamical since usually this nonlinear equation are considered on the whole space, then the phenomenon which we have here is the appearance of solutions with different structure with different spatial structure. For example, we can start with steady solutions which are more or less homogeneous. We can have solutions with some discrete symmetry, which effectively become periodic with some period. Then these roles can become more and more complicated, and we can have what is called disclination and dislocation, which are some kind of topological defects in this picture. So, in my opinion, one of the most important problems here is the classification of all this different type of spatial structure which can appear and all possible types of bifurcations which can happen when we go from one type of behavior to the other. And in this connection, I would like to discuss the notion which is known in the theory of dynamical system as computer-assisted proofs. So the first time when in the theory of dynamical system, when computers were used for giving rigorous proofs of some mathematical statement was again in Feigenbaum Universality, where where people constructed an approximate finite dimensional equation for the fixed point. Then numerically this approximate fixed point was found, its properties were discovered, were investigated, and then the rigorous theorem was proven which said that the whole original system has a fixed point which satisfies all needed solutions. And we can certainly, if we believe that computer gives correct results, then this is absolutely a rigorous proof. But from the other side, there are many cases where rigorous results are needed, computer-assisted proofs are needed, but nobody actually wants to do this. For example, it was the case with the Lorentz model, which I mentioned before. Lorentz model was observed numerically, again in a very convincing way, and only recently a student of Carlson, Farrell, gave computer-assisted proof of the existence of Lorentz attractor. So now it is a rigorous theorem that the Lorentz picture is really a rigorous mathematical picture. But people are not excited by this. Well, that we always believed in this. And so the future of these directions of computer-assisted proofs was not clear for many years. But it seems to me that in the partial differential equations, the role of these proofs, which go in parallel with numerical and computer experiments, will grow because people who study concrete examples which come from experiment always produce pictures and numerics which require some explanation on the level of theorems. And this will be some kind of important part of in the theory of dynamical systems, and especially in this part related to partial differential equations. Then I cannot refrain myself from spending 1 minute on one of the most famous problem in all these topics is blow up in three-dimensional Navier-Stokes system. So it is a remarkable theorem. It is a remarkable problem, and the majority of people believe that in this system the viscosity is strong enough, and therefore blow up does not exist. And there exists a much smaller group of mathematicians, especially of those who work on this problem, which believe that it is just quite opposite. And I also belong to this group. But I want to explain to you that from one side, the situation is almost the same as it was with the fifth postulate of Euclid. There was a lot of evidence that for each point there exists only one parallel line to the given line. From the other side, after yeah, it was absolutely experimentally assisted proof. Yeah, but from the other side, the future showed that it is not always true. And if it is not so for the three-dimensional Navier-Stokes system, then we really come to a very serious problem. What will happen with this system of equations? So there is a general theorem, a general result which was proven by Foyer, Stemmer, Maida, Kato, and Bialy, which says the following. If we consider the three-dimensional flows with periodic boundary condition, and U of k is Fourier coefficients of our solution. So U of k is three-dimensional vector for k, for each k, and k is the point of the three-dimensional vector. Yeah. For three-dimensional vector. Then the main result of the papers which I mentioned is the following, that all singularities which can happen for the Navier-Stokes system are connected with the infinity of the entropy, namely with the infinity of this norm. Is for Navier-Stokes with positive viscosity and without forcing. Yeah. So, for example, one can prove easily that if this sum is finite, then it is impossible that the force moment is infinite. Because if it is finite, then from the whole equation it follows that U of k decay exponentially with k, and all moments are finite. Therefore, if we accept the point of view that there is a blow-up at finite moment of time, then there is some value of vector U of k which corresponds to our flow at the moment of blow-up, right, for which this number, which is called entropy, is infinite. And from the point of view of the original phase space, it means that the flow U of x most possibly has singularity only at one point. And this is a local problem. We can formulate the problem about blow up of solutions in three-dimensional Navier-Stokes equation in just the following very simple way. Suppose that we have a sequence U of k for which the sum U of k squares is finite, but this sum is infinite. This is a point in our functional space. The question, is it possible to find initial conditions near this point with finite value of entropy of this norm, so that having this initial condition, we can come to this point after a finite interval of time? And this is a local question. Local question in the theory of the theory of dynamical system in infinite dimensional differential equation. So I shall finish.
It's local near singularity, so you can make potential singularity, you can make an expansion.
No, there is no forcing, it's just very concrete system of equations, but certainly we are near the points where it is infinite. But the energy is finite. So we want to study the dynamics of our system on a very small interval of time. So I want to finish with the formulation of the following hypothesis, which is based also on some ideas of renormalization group theory. I have absolutely no time to talk about this. And it says the following. The sequences U of k for which this can happen must satisfy to the following asymptotics. U of k decay at infinity as 1 over k squared. Only this type of asymptotic can appear at the moment of
There's a
symplectic.
relation near this point,
Yeah. So, yeah, and so unfortunately I have no time to talk about the third topic, but maybe there will be some possibilities on the Dead Sea.
Now we have 3 minutes break in the discussion.